Okay, so since it's already 3 o'clock, let's get started with the lecture. So, welcome everyone to week 9 of this TA session course for the course Optical Spectroscopy and Microscopy, Fundamentals of Optical Instrument Measurements and Instrumentation. And as you might already know, for the past 9 weeks, I am Arjun, who is the TA for this course. So, we are in week 9 now, which is like almost um, about two-third of the course has been almost two-third of the course is already over. So there are like 4 more weeks left. So the routine uh, of the course is pretty simple, as it is the case for the past 8 weeks. So I'll be going over a brief recap of the lectures that I've been taught in the past the week 9's lectures, followed by which I'll also be discussing some of the sample problems that I have curated. And after that, we'll be discussing the previous week's assignment problems. So in this case, for today's week, we will be discussing week 8's assignment questions. Uh, yeah, so since I can't see anyone in this room right now, so I'll just get started with this session. Just make sure once again if the session is recording. Yeah, it is recording. So I'll get started. So for the past 8 weeks, what we have been seeing is we have been slowly studying about light and how to apply light in lasers as well as in microscopy. So for the past in the initial weeks, we were studying about how light behaves when using quantum mechanical processes, and we were establishing the concepts of absorbance as well as fluorescence through quantum mechanics. And as we started discussing concepts in the later parts, the second half of the lectures, right from week 7, week 6, and week 7, we were looking at different types of lasers, such as your continuous laser and your pulse laser, how they behave. We were about to give quantitative and semi-quantitative definitions into how they work. And I think last week we were discussing about crucial processes such as your Q switching as well as your mode locking, which helps us get ultra fast pulse lasers. So this week will be an extension of the past 8 weeks, where we kind of um, entered a very fresh area. Uh, mostly the concepts that we are discussing in this week 9 were pertaining to your confocal microscopy, where we initially saw about the process of polarization as well as birefringence, where the course instructor initially started by giving the definition of polarization, how it depends on your extinction coefficient as well as your electric field as well as your magnetic susceptibility when it is in a field. And we also saw that your polarization will have linear components as well as your non-linear components. And we also saw about the concepts of your some frequency as well as a difference frequency, and how the concept of polarization follows your uh, momentum conservation as well. So we were looking at all of these materials, and we were also looking at birefringent materials, where we discussed the process of birefringence, and where we discussed that uh, materials can operate in the uh, second harmonics as well, where the second harmonics calculated from the first harmonics will be independent of your propagation direction, while your initial frequency will be dependent on the propagation direction. And after that, we went to confocal direction, where we saw initially about the lens equation, which you might already know, where we can draw a relationship between the length of the object as well as the length of the image using the length of the focal length. And coming back from like drawing concepts from the previous weeks, we also saw about concepts such as your beam width as well as your um, beam width as well as your beam window, where we saw that how the beam width should be large enough, and it should be as large as the objective lens that we are using in order to reduce the beam window, which will help us arrive at sharper images with good resolution. And we also saw about the concept of dichroic mirror, and I have mentioned I have inserted a schematic of how a dichroic mirror works. So a dichroic filter is a special kind of a filter where it allows uh, light of only a specific wavelength window or a specific bandwidth to pass through it, while it reflects back all the other wavelength all the other wavelengths outside that specific bandwidth. And in the dichroic mirror, this is a sample of how a dichroic mirror's profile will be, where we can see that this profile, where it shows almost 100% reflectance, is where your dichroic mirror operates, is the wavelength bandwidth at which dichroic mirror operates. Typically, a dichroic mirror profile will have transmittance values in the y-axis, but in this profile we have this profile which I have taken from the internet from a specific microscope's manual. The dichroic mirror's profile is given in the terms of reflectance as well. And we also saw that dichroic mirror is indeed a part of a larger value of larger category of filters called as interference filters, where the interference values, the bandwidth that needs to be called as a specific bandwidth, it needs to be a wavelength where it can do the process, where it can transmit more than 50% of the light. So in that case, it's called as the bandwidth. Those wavelengths the filter can actually transmit more than 50% of the light. It's called as the bandwidth of the interference filter. And we also saw how an ideal and a practical profile for a dichroic mirror will function, where the ideal profile for a dichroic mirror will be much more square in nature without the hinges here, while the practical range, due to several other factors, we'll be having this kind of gradual profile in this for the bandwidth. And in the last two lectures, we also saw about laser imaging systems, where we saw that there are specific properties that a laser needs to follow in order to get a good image. The first property being that the changes in contrast should be as a function of space. That is, the concept of spatial frequency should be validated for a specific laser. And in order for that to happen, the sampling rate of the laser should be greater than the half of the optical resolution of the microscope. And later on, we also went to understand specific optical instrumentation terms, where we saw about resolution, your sensitivity, as well as your width of your incoming laser, which this concept has been repeated over a couple of times in the past few weeks as well. And we also saw about the concepts of stage scanning microscope, where your sample will be there in the stage, and the stage will rotate while the optical beam, the imaging unit will be constant. And on the other hand, we also saw the opposite of the stage scanning microscope, where the stage will be set while the imaging module will be moving around in a raster fashion. In that aspect, we also saw a concept called as optical hinge points, where we saw optical hinge points as well as your temporal focus points and spatial focus points, where temporal focus points indicate that light beam from different time points tend to intersect at a common point, whereas spatial focus points indicate that light beams from different points on a lens, falling on a lens, will meet at the same point. They will intersect at the same point. And towards ending the lecture, we also saw about the concept of galvanometric mirrors, where when a lens is tilted, the light waves still tend to intersect at the same point, and this deflection angle is also dependent on the voltage of the galvanometric mirrors. So this is about a brief recap of the concepts that were taught in week number 9. So we can have a short doubt session in this with respect to this, where we can discuss if there are any doubts with respect to the past this week's lectures, or with respect to the past 9 weeks lectures. If people have no doubts, then we can start discussing the sample problems. Okay, if there are no doubts, we will start the sample problems. So question number one, why is a simple mechanical translation of a laser beam across an objective lens avoided in scanning microscopy? Why is a simple mechanical translation of a laser beam across the objective lens avoided in scanning microscopy? So in scanning microscopy, if we use an objective lens, what would happen eventually is that the corner, like the light beam which is at the corner of hitting the corner of the lens, they will undergo significant intensity loss compared to the center. So we saw the beam profile, we saw the intensity profile in the previous lectures, right? So as a result, at the corners we will not be getting a this thing. So this process is actually called vigneting. So the correct answer is it causes vigneting, artificial intensity loss at image edges. So question number two, the angular position of a galvanometer mirror is proportional to which quantity? We saw just in the recap that it's voltage. So angular position is proportional to the applied voltage. I'm just going over the answers because no one is in the room right now. So if you are watching it in YouTube, you can just pause it and you can think about it for a second. Question number three, what is the physical purpose of an optical hinge in a scanning system? What is the physical purpose of an optical hinge in a scanning system? So optical hinge, we know that whenever a light beam is tilted and it is it's fall on the any part of the lens, it is always filling the lens aperture. So the correct option is B. So the optical hinge is used to tilt the beam at the back focal plane while always filling the lens aperture. This is a pretty straightforward problem. What's the relationship between the focal spot size, which is omega naught, and the incoming beam width, omega in, is best described as? So we know that the larger the incoming beam width is, the smaller the focal spot size is. So it's inversely proportional. So the correct option is option B. Omega naught is inversely proportional to omega in beam, incoming beam width. Question number 5. Where must the scanning mirror be placed related to the scan lens to produce parallel beam translation? Where must the scanning mirror be placed related to the scan lens to produce the parallel beam translation? So we all know that from the lens law, like that if an object is placed on the focal length, then the beam will be collimated in laser, which is parallel in nature. So if you want to produce a beam which is parallel, then we should be keeping the lens at the focal length of the scan lens. So the correct option is option B. Question 6. Which beam movement pattern do galvanometers most commonly use to build a 2D image? So this is a straightforward question. If it's a 2D image, it's most probably raster scanning. So in raster scanning, what happens is the scanner uh, beam movement pattern is uh, in lines across a XY and then followed by Y steps. So raster scanning is fast X sweeps followed by Y steps. Question number 7. In confocal microscopy, what is the primary function of the pinhole? What is the primary function of the pinhole? So this is in correlation to all the light concepts and the focal length that we saw. So function of a pinhole is to have it as small as possible so that it can reject all the out of focus light. So the correct option is option B. to act as a spatial filter, rejecting out of focus light. Question number 8. Temporal focus points in a scanning system most accurately refers to what? And this we saw in the recap recently about spatial focal points and temporal focal points. So temporal focal points are those points where beams from different time intervals intersect. So correct answer is option B. Points where beams from different time intervals intersect, such as the scanning mirror. Question number 9. To achieve the highest possible resolution in a scanning system, the laser beam should be expanded to what? And this also we saw in the recap. So, to achieve the highest possible resolution, the beam in the omega naught, which is the focal spot size, should be very small. And if the focal spot size should be very small, then the incoming beam width should be very large. And the maximum size the incoming beam width can be is the size of the aperture itself. So the correct option here is option B. Match the full width of the objective lens aperture. The laser beam should be matching the full width of the objective lens aperture. And option 10. Optical sectioning refers to the ability of a confocal microscope to do what? So optical sectioning basically is it's a straightforward question. Option B is the answer. So it's a process where we image a very thin plane by rejecting the background light so that it appears as sections. So for this week, I have just had most of them are just theoretical questions because I didn't come with practical problems because this week's lectures was a very theoretical question. So that's all for the sample problems now. So before going for the discussion of the week 8's questions, if anyone has any doubts, they can shoot it up. Okay, in the case that no one has any doubts, we'll go to the sample problems. Sorry, not the not the sample problems, the assignment solutions. So even in this assignment problems, I saw that most of the problems are not numerical in nature. So I'll just be skimming over the questions in general. So in mode locking, what happens? This is a multiple select question, so more than one option can be correct. So in mode locking, options are we face we phase lock different wavelengths of light present in the cavity. We phase lock the different longitudinal modes present in the cavity. We phase lock different TEM modes present in the cavity. We lock the pump and the oscillator to operate in phase. And we know in mode locking that we lock the longitudinal modes as well as wavelengths, which correspond to the longitudinal modes, which correspond to different frequencies. So the correct answer is option 1 and 2, where we phase lock the different wavelengths as well as the longitudinal modes present in the cavity. So second question, Q switching and mode locking are different processes and both of them can be active or passive. And the other options are discussing that different processes or same process, and they're discussing that either of them can be active or passive. So the correct option is that both of them are different processes, Q switching and mode locking, because both of them are used for different purposes and both of them have active and passive modes. So the correct option is option A, different processes and both of them can be active or passive. Question number 3 is the minimum number of prisms required for complete dispersion compensation is how much? So for so this is a tricky question because for complete dispersion compensation we do not have any actual limit. We can use how much ever laser we want. So the correct option is there is no limit. We can also do it with 1 prism. So this is a very direct theoretical question. We have to find the wavelength of light used for exciting titanium sapphire to cause Raman value, which is 488 and 532. I should have mentioned here there is an MSQ question, sorry for that. It's a MSQ question and the answers are 488 and 532 nanometer. Question number 5 is, if a student has to design an ultra-fast IR laser with the requirement of high repetition rate, then he or she has to do what? So only when the question has a ultra-fast laser with a high repetition rate, the only question that the only hint that we should be getting here is that mode locking. So he or she has to choose mode locking as a mechanism of pulse generation. Option A is the answer. Question number 6. The repetition rate of the laser can be altered using the end mirrors. Choose the correct statements below. So the repetition rate of the laser can be altered using the end mirrors. Choose the correct statements below. So altering the position of the end mirrors changes the repetition rate. If not, it cannot be altered for a given laser. Changing the wavelength alters the repetition rate and changing the power rate changes the repetition rate. So it's also a straightforward question. The answer is that if we alter the position of the end mirrors as well as the wavelength, it changes the repetition rate. So the minimum number of mirrors necessary for coupling the laser output along the optical axis. So this is also a follow-up tricky question compared to the previous question. So the minimum number of mirrors that we need is 2. So the correct answer is option 2, option A. 2. So eighth question, it's a numerical problem. So a collimated beam of light on an optical bench, a collimated beam of light on an optical bench first passes through a lens of focal length 8-10 centimeter. After about 8 centimeter, there is a prism which totally internally reflects the beam, which then passes through a 10 centimeter focal length lens kept at 25 centimeter from the first lens. Estimate the diameter of the beam. So this is a bit of a tricky question, which we can try to solve mathematically. So basically, okay. Yeah, let's just briefly have this as a small setup. So we have a collimated beam of light. So it will be, and I'm not drawing it exactly parallel. So I'm not drawing it exactly parallel, but I think you can just get the concepts. So there's a parallel beam, and after, uh, so the focal length is 10 centimeter. So let's just keep this point as the focal point, which is 10. Okay. And it passes through the lens. Yeah. And okay, let this point be 10 centimeter. So, and after that, after about 8 centimeter, okay, I think, yeah. So the focal length should be somewhere here, around here, 10 centimeter. The beam is actually passing from here. Yeah, like not exactly like this. Should have some width here. So after 8 centimeter, there's a prism which totally internally reflects the beam, and then so total internal reflection happens. So it neither deflects nor has anything. So it just passes through as it is, and then it passes through a 10 centimeter focal length lens kept at 25 centimeters from the first lens. Yeah. So this total length is 25, but its focal length here it's 10. So, and this length is also 10. It's not up to scale, but I hope you can just follow me here. So this beam of light, it passes through this lens, and we have to estimate the diameter. So once it passes through the lens, since it does not have any friction, it just gets collimated and it passes through parallelly. So we have to find the ratio of this to this. So with respect to 1 and with respect to 2, the diameter of 1 and 2, we have to find the ratio between them. That's the whole concept of this problem. So how do we move around doing it is that using this focal length information. So we know that focal length of the first lens is 10. So from that, if the and we know that the distance of the first lens from the second lens is 25. So if we just simply do the math, the distance of the focal length of the first lens with the second lens is 15 centimeter. So that we already know. So what we have to do is we have to apply this formula, which is saying yeah. So the diameter is directly proportional. Diameter of the beam. We know that the diameter of the beam is directly proportional to the beam of the width at the focal spot size. So we are just moving all of them to the same side. So it should be diameter of the beam divided by the focal spot size should be equal to the diameter of the second beam divided by the focal spot size at the starting region, because it's starting at the focal the beam hitting the lens is starting from the focal point of the first lens, so it's 25 minus 10. So we have to find d2 here. So if I have to find d2, we have to shift 15 here. So d2 will be 15 by 10 of d1, so which will be 1.5 times d1. So it just means that the beam is getting magnified 1.5 times. So the correct answer will be here. Correct answer here will be magnified by 1.5 times. So I hope you guys can get the idea of this thing. If not, anyways, I will be uploading this in YouTube, so you can replay this, um, how to solve the problem, and then go around it. Once again, I'll just yeah. So next question: lenses typically do not require kinematic mounts. Choose the correct option about the statement. So we have to choose the correct option about whether lenses typically do not require kinematic mounts. Options are incorrect statement, we require kinematic mounts. Option B is because we do not change the incident angle. Third option is the incident beam front need to be normal to the lens surface. The fourth option is lenses are refractant components, so they do not need them. So the correct option is So the correct option is two options, because we do not change the incident angle. So incident angle remains constant. So they do not require kinematic mounts. And then the incident beam front needs to be normal to the lens surface. The last question is, if a kinematic mount rotates the mirror from the equilibrium position by x degrees, the light will tilt by an angle of how much degrees? So this can also be solved mathematically. So sorry. Yeah. So let's just assume this as the lens and this to be the optical axis. So we are having a line which is passing through the lens like this, and the angle can be think there is a small glitch there. So okay, so let the angle be here x. Sorry, actually, oh, sorry. So you can consider this for the question of mirror as well. You don't need to generally do it for a lens as well. So 1 second, I'll just draw it for the mirror itself, so that it will be much more easier to understand. Yeah. So let this be a mirror, and let this be a normal to the surface, and this can be a line, and uh, this can be your incident ray, and this can be your sorry, this can be a reflected ray. So this is obtaining an angle of, let's just say, x. I'm just simplifying the problem for you. So yeah, yeah. So let's just say it can be theta. So what we are doing right now is we are tilting the mirror by an angle of x degrees more. So it just means that there is a new normal, and so let this be x here, and the incident light here, and it will be having a different reflected light. And so we know here that if the incident angle is theta plus x, then the reflected angle will also be theta plus x. So the difference between both the angles, the initial angle and the this thing is uh, theta plus x, theta 2 theta plus 2x minus 2 theta. That will be the difference. So it will be 2 theta plus 2x minus 2x. So 2x will get cancelled. So it will be 2 theta. So it will be if the mirror is rotating by a position of 2 degrees, then the light will also tilt by an angle of 2x. So the correct option here will be 2x. So that's all the discussions for uh, this week's assignments problems is. So till the we have some time more to discuss about the uh, questions. So if you have any questions, we can discuss it till the end of the session. Else, thank you all for coming to the session. Uh, and we'll see you. I'll see you in the next TA session, week 10's TA session, next Sunday, 29th March, from 3 p.m. to 5 p.m. Yeah. Uh, but till then, till the session is over, the session will be open for doubts. So if anyone has any doubts, they can ask. If you don't have, if you can't open your mic, you can open the chat box and then ask the questions. So if there are no doubts, we can meet on 29th March next Sunday from 3 p.m. to 5 p.m.